Once again, back from the break, and now what we're going to talk about is a little bit of the inverter design layout. It's basically this reflects some modern silicon chip manufacturing. Of course, there's many more steps required to actually create an inverter, but in general the process is built up layer by layer. So materials are deposited or grown, patterned using a relatively complex photolithography type process, so it's sort of like making an old photograph. And each layer is formed using photosensitive material, and it creates a pattern mask. There may be many hundreds of steps, and 20 to 30 masks required to produce a modern silicon chip, perhaps even more than that. Each group of steps, though, does have an awful lot in common. So just to sort of manage some of that complexity, there's a number of design rules, and that has to do with laying out designs. So designs generally you try to create them so they'll occupy the smallest possible area, and as a consequence you typically get the benefit of being as fast a device as possible. You have to put some constraints on how small the circuit can be, and those might be imposed by the fabrication process, the technology, or the characteristics of the circuit and devices themselves. Design process would take far too long if you were to calculate or simulate all possible configurations to achieve a possible smallest area. The problem is likely NP complete, so some optimization and compromise is required, and that sort of has led to the role of design rules. For example, design rules might specify minimum width of spacing between layers of materials. It may try to minimize the area used while trying to guarantee that you could fabricate the device. So an example might be you're not allowed to put two pieces of metal too close together. You have to separate them by something, otherwise there may be a risk of them effectively coming in contact with one another when it's being manufactured. Often referred to a minimum feature size, or lambda, and then some design rules can be based on multiples of that constant factor. More current technologies sort of recognize that traditional scaling laws are limited, and you sort of have to have an independent specification of the level, spacing, and sizes. And what that implies is that you don't have a universal scale factor, but you have a scale factor that depends on the different layers and levels. This is sort of the notion of a scale device, and you can see some of the things that are scaled here, some a little bit more obvious than the other. For example, the wires are made thinner, the gate dielectric is made thinner. That's represented by this T-ox divided by lambda. Some things that are less obvious, you're to scale the voltage by lambda. The length of the gate is scaled by lambda. You'd appreciate that because it's going to make the device faster. The depletion region is scaled by lambda, so consequently you have to increase the number of dopants down there. And these things may or may not be all that possible to do or that easy to do. So in general, here's what you have to scale: a voltage and oxide, wire widths, gate widths, diffusions, and substrates. And there's the scale factors represented by lambda. And these are the results you get. Obviously, if you make the device smaller, you're going to expect the density to go up, so it goes up by lambda squared. The device has a higher speed. This is sort of a consequence of it looking like an RC kind of time constant. And if you take into account all of the factors, such as these up here in the scaling laws, you'd see that the speed goes up by a factor of lambda. You do get lower power per circuit, which is 1 over lambda squared. That's a good thing, but the power density is roughly going to remain constant because the density is higher than the lower power per circuit, and they cancel out one another. These things aren't particularly obvious to calculate. I'm sure everyone can sit down and do that. Once you work out some of the basic performance equations we'll see later, you'd see how the scaling impacts these types of things. Here are some examples from IBM. So these were real development test masks from Doug Buchanan a few years back. Just point out a few things here. We've mentioned before, a mask is a fundamental component of building these devices, and it's a photolithographic technique. And there's a thing known as polarity. So a positive shape means that you're leaving something behind, so that might be the polysilicon level for the gate. A negative would mean that you're basically creating something like a contact hole. You're removing something from the surface. And then there's some details that, if you're interested in, you can certainly burrow into them in as much detail as you like. I'm certainly not going to do that here. Just going to talk again a little bit about some of the design rules, and in particular sort of have a graphical representation of them. Here's one in particular that would be kind of obvious. If you're going to make a contact cut, you want to have the contact cut, make sure that it is smaller than the region you're putting the contact hole into or on top of. Another one that might be kind of obvious is that if you're building a transistor, you want the polysilicon layer to extend out beyond the thin oxide layer. If you didn't do that, there's a possibility you'd have a device which would basically have a conducting path from the source to the drain. There's a few other sort of graphical representations here. These are some design rules that came out of a 250 nanometer technology node process, so pretty old by today's standards, but still multiple levels of metal. And some of the things you can see as you go through the lower levels of metal is they're allowed to be closer together and they're thinner, but as you go up through the sort of the metal hierarchy, you see at the end here they have to be spaced quite a bit further apart, and they have to be a fair bit wider. And some of those reasons have to do with the fact that you're routing these on more irregular type surfaces. Perhaps they have to handle higher current densities, and if they're wider, they're also going to be a little bit less resistive if they have to go any distance. So as a general rule of thumb, the metal would be wider and further apart as you go up through the metal hierarchy. Here's a couple more pictures from design rules of 250 microns. 0.25 microns or 250 nanometers. So some of the things I might ask you is, what here can you identify? Well, if you went back through those other layers, hopefully you can identify a few things. Some are labeled, some aren't. But hopefully you can recognize this without too much effort as being an inverter. And, based on our little rules of thumb before, where the mobility of the P-type was less than that of the N-type, it's wider, so we expect to see that wider by about a factor of 2. Some of the things you might be curious about, why there'd be multiple contact holes. That would probably be a design rule that would maybe keep a bigger hole area from bloating and sort of keeping much of the processing kind of uniform across the device. So there's probably, if you built a modern integrated circuit, there's probably like sacrificial regions which will have materials present or not present, even though they may have no function whatsoever. That's about it for that slide. Here's a couple more examples just for the design rules for contacts and select layers. And then a couple more examples over here. And again, it would sort of specify what these overlaps have to be, what the metals would have to look like, and what types of overlaps you would have if you're connecting up, let's say, these two vias here to make a better contact between this polysilicon layer to this metal layer. So we get to something that looks like a layout. It's pretty old, but certainly from this figure you should be able to at least reverse engineer it and maybe identify a few things. It's not completely labeled, which doesn't help, but this up here is VDD, this down here is ground, and this here is an output. So you can sort of start putting things together here and recognizing that perhaps this is the source of the N-type transistor, and then I've got 4 transistors in series, and when I go up to this region here, I start to see that I have 4 transistors in parallel. So you hopefully recognize that as a 4 input CMOS blank, and you fill in the blank. So what design rules are useful for? Certainly they're at the lower levels of implementation, help you fabricate what you want to fabricate. It's really not within a IC designer's responsibility to worry about those low-level design rules, but you should at least know they exist and how they might affect your design. This is just a discussion of a parasitic. A parasitic is just something that you didn't design for, but it's present, and it used to cause this problem called latch-up, and I'll give you an example of that in a couple of minutes. But basically it's just a parasitic circuit that's formed as a consequence of all these different layers that were used to make the inverter in a CMOS technology, and it's certainly been reduced in any kind of significance through materials processing and design rules, probably likely, as you may have guessed. So here's an example of a couple of parasitic dipolar transistors which are present if you just built an inverter in that type of a substrate for the N-type device and a well for the P-type device. So I'm not going to go into any detail here at all, but to sort of illustrate what happens, this is what that parasitic circuit looks like. If you happen to get some substrate current, and you might happen to do that because maybe you've turned a gate on or off, and it's basically looks maybe like a propagating voltage pulse down a bit of a transmission line. It may have an overshoot when it meets its terminating impedance, and these overshoots and undershoots can sort of cause substrate currents. So you get a little bit of substrate current, and what you see happen here, it'll turn on this transistor. So you're basically biasing this transistor and turning it on, and it turns the other one a little bit stronger, and it turns that one on a little bit stronger, etc. Before you know it, you have a conducting path through your substrate from VDD to ground. So that's when the device would latch up and tend not to function anymore, and potentially could have destroyed the device. So anyway, some of the things that the designer can do, they can certainly use design rules to try to control something like decoupling the devices so they're far enough apart so that the substrate resistance is high enough so that you don't end up I guess the substrate resistance will be low enough so that you don't end up turning on those parasitic polar transistors. Or you could basically decouple the PN-PN-PN pair, and that's sort of known as this silicon and insulator, or some of these twin tub processes. So certainly don't have expertise in that area, but can appreciate that by modifying the design a little bit, you might be able to reduce some of those types of problems. So in any event, latch up at one time was a problem, certainly addressed through materials and design rules. But you might say that you have similar problems today, virtue of the consequence, rather a consequence of the fact that devices are so small. So you might get things which are related to radiation-induced soft error. So that might be an ionizing particle that creates some kind of a disruption to a device. A capacitor might be only storing a small bit of charge. And partial solutions, which would be now at the design stage, would be to make crucial devices radiation hard, or perhaps some soft error blocking flip-flops. And what that means is, since you already have some scan circuits perhaps present on board, you could perhaps have redundant copies of a flip-flop and then just have an XOR function which would give you an indication of an error had occurred due to perhaps an ionizing piece of radiation. So anyway, a summary for this chapter is we looked at the CMOS inverter in considerable detail. DC characteristics were derived from the basic MOS transistor characteristics. Transfer curve was then derived from a load line analysis. We looked a little bit at transistor sizing and some temperature effects. We introduced the concept of noise margins, or reintroduced them because they'd have been familiar to you, and sort of noted why CMOS had pretty good noise performance. I looked just briefly at the fabrication of the CMOS inverter in a oversimplified detail, but you have to basically build a little CMOS inverter as part of the first assignment, so it'll resemble something like that we discussed. Looked at some design rules and sort of provided some rationale for them, and gave an example of a parasitic device. And that's it for chapter 3.